3.4, linear and angular speed. So linear speed, suppose that a point P moves at a constant along a circle of radius r and center O. The measure of how fast the position of P is changing is the linear speed. If v represents linear speed, then speed equals distance over time, or v equals s over t, where s is the length of the arc traced by a point P at time t. So speed is distance over time, but when we're talking about a circle, v is s over t, sector length over your time, because we're talking about how fast it's going and rotating around the circle. Angular speed as point P moves along the circle, ray OP rotates about the origin. The measure of how fast angle POB is changing is its angular speed, omega equals theta over t. So the change of speed is going to be your angle over time. That makes sense though, because isn't that the change? Because that's how much you're opening. Alright, so here are some formulas that you absolutely must memorize. Angular speed, which is theta over t, and you have to be working in radians. Then you have linear speed, which is s over t, r theta over t, or r omega. So you can use multiple formulas here, but you'll figure out how to use them and when to use which one because of what we have. So suppose the point P is on a circle with radius 10 centimeters and ray OP is rotating with angular speed pi over radians per second. A. Find the angle generated in P in 6 seconds. B. Find the distance traveled by P along the circle in 6 seconds. And C. Find the linear speed of P in centimeters per second. So we're going to be using stuff in 3.4 again and again and again throughout this semester because we need to know how to switch between speed per second, per centimeters per second, per mile per hour, stuff like that, units of measurement. So let's find the angle generated by P in 6 seconds. So A. We need to find angle generated when we're given stuff. So we have a few things. We have radius, and we have angular speed of pi over 18 radians per second. Alright, so we're given angular speed and we're given the radius. So remember, angular speed represents that omega. So we're given omega, and we're given the radius. So in part A, we want to find the angle generated in by P in 6 seconds. So in A, we're given 6 seconds for time, and we want to find the angle generated by it. So angle means theta. We don't know it. So if we have time and we need to find theta, we're going to be using the formula omega equals theta over t. So we have our omega, which is pi over 18, and that equals theta over t, which is 6. We cross multiply, so we have 18 theta equals 6 pi, divide by 18, so we have theta equals pi over 3 radians. So that is the angle that's generated by this ray in 6 seconds, pi over 3 radians. It's rotating really slow. So now, pay attention to what we have. Now we have r, we have angular speed, which is w, and now we have theta. Now we have theta. Find the distance traveled by P along the circle in 6 seconds. Alright, so B, we're trying to find our distance. Distance along a circle is sector length. Sector length is S equals R times theta. Do you notice in here it doesn't even have that formula? Because that's something that we've learned. It's something that we know and need to apply whenever we see it. Whenever we see distance along a circle, sector length, arc length, we're talking about S equals R theta. So we need to find S. We have our radius. It was given, thankfully, which is 10. And then we just found theta. We literally just found our theta of pi over 3. So we have 10 times pi over 3, so our S is just 10 pi over 3. Alright, so let's pay attention to what we have. We have theta, we have S, we have R, we have W. Find the linear speed of p in centimeters per second. So linear speed, not angular speed, linear speed is represented by these formulas right here. So we know we're going to have to use something with v in it. So we know it's going to have to be v equals something. So let's pay attention to what we have. So we want to know in centimeters per second. So we can't use the first one because we don't actually know how long we're doing this for. So we can't use it. Let's see if we can use any other ones. We can't use this one because in part C it doesn't tell us how long we're doing it. We can't. We don't have t in part C, so we can't use that either. So let's see if we can use the last one. We have the radius and we have omega, so we can use the last one of our w. So let's go ahead and plug in what we have. So we have v equals the radius, which is 10, times our omega, which was pi over 18. We simplify and we get v equals 5 pi over 9 centimeters per second. A belt runs a pulley of radius 6 centimeters at 80 revolutions per minute. Find the angular speed of the pulley in radians per second. Alrighty, part A. So 1 revolution is 2 pi radians. We know that. It's 360 degrees, which is 2 pi radians. And 1 minute equals 60 seconds. We know that. Why are we talking about this? Because we're talking about revolutions and we're talking about minutes here, and we need to switch it to seconds. That's why we're talking about that. Alright, so we know we can find speed. We can find our omega, because we're talking about angular speed. But we have to set this up as a proportion because we're working with 80 revolutions per minute, but we need per second. So we're talking about 80 revolutions per minute. So 80 revolutions per minute. We would, if we wrote that in English, it would be 80 revolutions per minute. So that's why we write it this way. It's just a fraction. When you say per, it's a fraction. And then we're going to multiply that because it's a proportion. So we know that 80 revolutions, that's compared to how many revolutions? A revolution is 2 pi. 2 pi represents 1 revolution. So this right here is converting the revolutions to what is a revolution. Right? It's 2 pi. That's what we're converting that to. Then we need to convert minutes to seconds. So we know that 1 minute equals 60 seconds. Alright, so from here we multiply straight across. So 80 times 2 times 1, we get 160 pi radians. It's radians because we're talking about 2 pi here. And that's over 1 times 1 times 60, 60 seconds. So we get 8 pi over 3 radians per second. Another way you could have done this, another way you can think about it, because we all think differently, so another way we can think about this, I'll do it in red. Or what you could have done is you could have done, say, okay, so 80 revolutions in 60 seconds. Because it's 80 revolutions per minute. So a minute is 60 seconds. So that equals 4 over 3. So you have 4/3 of a revolution per second. So a revolution is 2 pi, which we would get 8 pi over 3 radians per second. Alrighty, part B. Find the linear speed of the belt in centimeters per second. So we have a few things. We have our omega, so we have W, and then we also have the radius. We have the radius, which is 6. So we have a few things. We have R and W, and we need to find V. Remember, linear speed always represents V. So we're going to be using one of these V equations. We have nothing about S. We don't know theta. So we're going to be using V equals R omega. So we have V equals our radius. Remember, our radius was 6. We just found our W, which is 8 pi over 3. When we simplify, we get 16 pi, but that's not centimeters per second. We don't know what 16 pi actually is, so let's plug it into our calculator. So 16 times pi, we get V is approximately 50.2654825. It goes on forever. So we need to round this using significant digits. So you see how it gives 86. Those are one significant digit. So to round this using one significant digit, it would be 50 centimeters per second. All right, example 3. A satellite traveling in a circular orbit 1,600 kilometers above the surface of Earth takes 2 hours to make an orbit. The radius of the Earth is approximately 6,400 kilometers. Approximate the linear speed of the satellite in kilometers per hour, and then approximate the distance the satellite travels at 4.5 hours. So the first thing we need to do is find the radius from Earth to the satellite. So Earth to the satellite, that's this right here, because that's what we're talking about orbiting, is the satellite. So the radius is 1,600 plus 6,400, which is 8,000 kilometers. So now we have our radius from the center of the Earth to the satellite. We have the angular speed. We might not know it, but we actually do have the angular speed. So it says the satellite is traveling 1,600 kilometers above the Earth's surface, and it takes 2 hours to make an orbit. So the angular speed is 1 orbit per 2 hours, and it can be converted to radians. So we know that we can convert this to radians because one orbit is one rotation around the Earth, which is 360 degrees, which is 2 pi. So we can find the linear speed. So linear speed, if we go back to our formulas, that's the W one. So our formula is theta over t. So theta is one orbit every 2 hours. And then we need to multiply that by 2 pi because we want to know what is that in radians. What is that in radians? So when we simplify this, we just get pi radians per hour. That's our angular speed. But doesn't that make sense? If we're doing one orbit per 2 hours, aren't we doing a pi radian per hour then? If it takes us 2 hours to do 2 pi, it takes us pi every hour. So now we have our angular speed of pi radians per hour, but we're not asking for angular speed, we're looking for linear speed. We're looking for linear speed. So linear speed, we need to use one of these formulas. V equals S over T, R theta over T, or R omega. So what we have radius, and we just found W, so let's go ahead and plug it in. So we're going to be using the formula V equals R angular speed, so we have the radius, which is 8,000, times the angular speed, which we just found, of pi. So that simplifies to 8,000 pi, which is about 25,000 kilometers per hour. That's our linear speed. We're at 25,000 kilometers per hour. Why do we round to two significant digits? Because it gave us two significant digits the entire time. Approximate the distance the satellite travels in 4.5 hours. So if we know that the speed is 8,000 pi, wouldn't we just do 8,000 times 4.5? Yeah, right? Because that makes sense to do that. But let's explain using formulas. So if we want to approximate the distance the satellite travels in 4.5 hours, distance around the circle, because we're going in a circle, we want to know the distance we go around in a circle. That's sector length. So we have sector length, we know that is r times theta, but we do not have a theta. We do not have an angle of this satellite whatsoever. We do not have theta. So let's see if there's a formula we do have where S is in it, and what we already have. So remember, we have S, we have V, we have T, we have omega, and we have R. So let's see what we do have. So we need to find S. So everything with S in it, that's the only thing with S. We have V, we have T, we need to find S, so we can use this formula. We're going to use the formula V equals S over T. We can get S by itself, so we'll have VT equals S. So our V is 8,000 pi. We got it from here, 8,000 pi. And then our time is 4.5 hours, so we get S is approximately 110,000 kilometers. We round to 110 because two significant digits.